In this lecture, we're going to discuss the second type of energy level diagram, which is orbital diagrams. Orbital diagrams are more informative than electron configurations, but the best way to make them is to write the electron configuration first and then fill in the orbital diagram. The orbital diagram describes very specifically how electrons are distributed within individual orbitals using arrows to denote spin. So the best way to illustrate this is to just give you a bunch of examples. Let's take boron. Boron is a relatively small element, only 5 electrons. And if we wrote down its electron configuration, it would be 1s2, 2s2, 2p1. The orbital diagram represents each orbital as a set of parentheses. So here's the 1s orbital, here's the 2s orbital, and then 2p has 3 individual orbitals within that subshell. So I'm drawing 3 sets of parentheses for the 3 2p orbitals. Now we fill in the electrons using arrows to denote spin. So I'm going to fill in the 2 electrons in the 1s orbital with an up arrow and a down arrow. Remember that if 2 electrons share the same orbital, they have to have opposite spin. So showing the arrows in the pointing in the opposite directions captures the idea that they have opposite spin quantum numbers. Same for the 2 electrons in the 2s orbital. I'm showing them as an up arrow and a down arrow, where each arrow represents 1 electron. The 1 electron in the 2p orbital, I'm just going to arbitrarily put into this 2p orbital here. Now, what happens when we have carbon? Carbon has 1 more electron than boron has, and its electron configuration looks like this. So I'm going to write, once again, the parentheses representing my 1s, 2s, and 2p orbitals. Now I'm going to fill them in with arrows denoting the number of electrons. So here are my 2 electrons in the 1s orbital. Here are my 2 electrons in the 2s orbital. Now in the 2p orbital, I have 2 electrons. So I'm going to put 1 here, but now here's the tricky part. The second electron, I don't want to put in the same orbital as the first one if I don't have to. Remember that electrons repel each other, and they want to try to avoid that repulsive interaction if they can. So since the 2p orbitals are all degenerate, the second electron is going to go into a different 2p orbital. This is because of Hund's rule. Hund's rule explains what we just did with the second electron in the 2p shell of carbon. It explains that within a given sublevel, like the 2p sublevel that we just saw, the order of filling maximizes the number of half-filled orbitals to avoid electron-electron repulsion. Maximize the number of half-filled orbitals with electrons of parallel spin. So you see what I just did in that example a moment ago. Here, I'm half filling the orbital and those electrons have parallel spin with each other. And the whole reason for this is that this avoids electron-electron repulsion. Electron-electron repulsion, resulting in greater stability. So what you want to do when you're drawing orbital diagrams is you want to half fill half of the orbitals first, and then pair up the leftovers. Let me show you another example. Let's do iron. So iron is an element number 26. Neutral iron will have 26 electrons. You may recall from a previous lecture that we can write its electron configuration, we can abbreviate it as the electron configuration of argon, followed by 4s2, 3d6. Okay, so I'm going to represent the argon in the orbital diagram with just an abbreviation kind of showing that this is the inner shell electrons. There's one 4s orbital, but there are 5 3d orbitals just because of the multiplicity of the 3d subshell. So I'm going to write all 5 of them here. 1, 2, 3, 4, 5 sets of parentheses to represent the 5 3d orbitals. So let's fill up the electrons now in our orbital diagram. The 2 electrons in 4s are easy to put in, but now I have to contend with the 6 electrons in the 3d sublevel. So I'm going to put 1, 2, 3, 4, 5. I half fill the orbitals first, and then for the 6th one, I have to start pairing them up. So the rule of thumb when you're doing these orbital diagrams, in order to obey Hund's rule, you want to fill half the orbitals first in the sublevel. Then you want to pair up the leftovers. So Hund's rule explains some unusual electron configurations. Let's look at chromium 24. The electron configuration for chromium is argon followed by 4s1, 3d5. That is a very weird electron configuration, okay? It's not what you would expect, which is probably, if you were just doing this, you would write 4s2, 3d4. So why is this observed? Hund's rule kind of explains why. Hund's rule explains why this electron configuration is the one that's observed. Let's draw the orbital diagram for chromium. Here's just the argon's the abbreviation for argon's inner shell. And then I'm gonna make a 4s orbital and then the 5 3d orbitals. Okay, so let's start filling up the electrons in chromium. I have 24 electrons total, and 6 of those 24 electrons are going to be in the outer shells. So 1, 2, 3, 4, 5, 6 is what we actually observe. The reason why this one dominates is because imagine if I were going to put both electrons in the 4s subshell here. The cost of spin pairing those electrons, the energetic cost of putting them in that same orbital, exceeds the difference between the 4s and the 3d subshells. So 4s and 3d are very, very similar in energy, and it actually would cost more energy to spin pair the electrons in the 4s orbital than it does to just actually put them all in their own orbital. So this is going to be the more stable arrangement, okay? This avoids the spin pairing energetic cost. Okay, so half-filled subshells are going to be particularly stable. And you actually see other examples of this in elements from the periodic table. So it's kind of a theme that you see again and again, that half-filled subshells are kind of special. They have special stability. So let me give you, well, here's just another example. Another kind of weird element in the periodic table is copper. Copper is element number 29, so neutral copper would have 29 electrons. And its electron configuration is a little bit surprising. It's 4s1 3d10. Not what you would expect. It's not 4s2 3d9. So that's just kind of a weird element with an unexpected electron configuration.